Okay, let's talk about light. It seems so simple, right? But what is it, really? This one little question sparked one of the biggest, most epic debates in the entire history of science. So we're going to dive right into this scientific detective story and see how the absolute giants of physics wrestled with it. All right, here's our game plan. We'll start with the two main theories that were duking it out. Then, we'll check out some of the crazy things light does, like how it can interfere with itself and how it bends around corners. And finally, we'll get to the verdict that, for a time, seemed to settle everything.
So, first up, let's set the stage for the Great Light Debate.
I mean, really think about it. The very stuff that lets you see everything around you, what is it made of? Is it like a stream of tiny microscopic bullets shooting out from a light bulb? Or is it more like a wave, like ripples spreading across a pond? This was the huge question, and believe me, the debate got intense.
You basically had two teams in two corners. In one corner, you've got Team Particle, and their captain was none other than Sir Isaac Newton. I mean, the guy was a scientific rock star. His big idea? Light is made of these tiny little bits, these discrete particles. And in the other corner, you have Team Wave, led by the brilliant Dutch scientist Christian Huygens. He was convinced light wasn't bits at all, but a smooth, continuous wave rippling through space.
Now, given Newton's reputation, you can probably guess which idea was the frontrunner for a very long time. Let's dig into his particle theory. So, if you look at the timeline, Newton drops his theory in 1675. Huygens comes back with his wave idea just a few years later. But then, nothing. For over 100 years, the debate just kind of simmers. The technology just wasn't there yet to really test things. That is, until 1801, when one crucial experiment came along and basically blew the whole thing wide open. Newton's theory, which he called the corpuscular theory, was beautifully simple. He said, look, light is just a bunch of tiny particles, which he called corpuscles. They shoot out in perfectly straight lines. And different colors, well, those are just particles of different sizes. Simple. And you know what? It worked. It perfectly explained why light bounces off a mirror, that's reflection, and why it bends when it goes through water or glass, that's refraction. So for a long time, it seemed like Newton had it all figured out. But there was one little problem, a critical flaw hiding in the math. And this is the killer. According to Newton's theory, light should actually speed up when it goes from air into something denser like water. It was a key prediction. But when scientists could finally measure it, they found the complete opposite. Light actually slows down in water. Uh-oh, that was a huge, huge problem for Team Particle. So with Newton's theory on shaky ground, scientists started to think, hey, maybe we should take another look at that wave idea. So let's dive into Huygens' wave alternative. The key idea for Huygens is something called a wave front. The easiest way to picture this is to think about dropping a rock in a calm lake. You see those ripples spreading out in perfect circles? Each one of those circles is a wave front. Huygens said, that's it. That's how light travels. But how does the next ripple form from the last one? This is where Huygens' principle gets really clever. He suggested that you can think of every single point on a wavefront as its own little source, creating its own tiny little circular wave or wavelet. And the next big wavefront is just the line that touches the front edge of all those little wavelets. It's a really cool way to visualize how a wave keeps moving forward. Okay, so it's a cool idea, but to really beat Newton, Team Wave needed a knockout punch. They needed to show something that light does, that particles just couldn't do. And that's where interference comes in. So let me ask you, what happens when two beams of light cross paths? You might think they'd just get brighter, but the answer is way cooler, and it's the key to this whole mystery. This is where things get really, really weird. If two waves meet up perfectly, in sync, crest to crest, they add up and you get an even bigger wave. For light, that means it gets brighter. We call that constructive interference. But what if they meet completely out of sync? Like the crest of one wave hits the trough of another. Well, they completely cancel each other out, and you get nothing. Darkness. Think about that for a second. Light plus light can actually equal darkness. How wild is that? And this isn't just some abstract idea. This is the smoking gun. In 1801, Thomas Young did his now legendary double-slit experiment. He shone light through two tiny slits, and what he saw on the screen behind them was a pattern of bright and dark stripes. That's the interference pattern. It was proof. There's just no way for particles to cancel each other out and create dark spots. This was something only waves could do. Okay, so the case for team wave is looking pretty strong. But there was another weird thing light does that really didn't fit with the whole particle idea.
It's called diffraction. And you've actually seen this. If you look really closely at a shadow, the edge isn't perfectly sharp, is it? That's because light waves actually bend a tiny bit as they pass by an object, spreading into the area that should be pure shadow. Now, if light were just tiny bullets flying straight, that wouldn't happen. But waves? Yeah, waves bend around things all the time. Just think about sound waves bending around a corner. So the evidence is in. It's time to head to the courtroom and get the verdict on light.
All right, let's look at the scorecard. Reflection, check. Both theories got that. Refraction, check. Both got that too. But then, interference? Nope, that's a big miss for Newton's particles, but a huge check for Huygens waves. And diffraction? Same story. A fail for particles, a pass for waves. So it looks like a slam dunk for the wave theory, right? But take a look at that last row, the photoelectric effect. Let's keep that in mind.
And based on this evidence, for more than 100 years, the case was considered closed. The debate was over. Light is a wave. That was the undisputed answer, and science moved on.
But here's the thing about science. Just when you think you have it all figured out, something comes along to mess it all up. Remember that photoelectric effect I mentioned? Well, it turns out that Huygens' amazing wave theory had absolutely no explanation for it. It was a brand new mystery, and it would turn out that the great light debate was far from over.